So here we are on a website called falstad.com that I found. It has a great applet for playing with Fourier series for well-known functions like sine and cosine. So let's play with this. Here's a graph of a sine wave, and I'm going to turn on the sound here so you'll hear what a pure sound wave sounds like. I've got the frequency set to 440 Hertz right about, which is a common frequency used in music. I'm not sure how loud this will be if you're listening on headphones, so you might want to be careful. I'm going to click it. Ready? 3, 2, 1. Okay, so that's a basic sine wave. Kind of sounds like a flute, maybe. What do you think a cosine wave will sound like? Ready? Not much difference. It's just when the pressure wave gets to your ear, maybe a little sooner, but that's also affected by how far you're sitting from your speakers. And so our ears are not really built to handle telling the difference between the phases of sounds in that particular way. So that's fun. What about a triangle wave? Does that look a lot like a sine wave? Let's play it here, and I'm gonna... So before we play it, let's look at it. Down here it's showing me the spectrum, and it's actually summing up sines and cosines, which I'll talk about later. And it's saying there's a lot of amplitude for this one, cosine, and none for that sine. And then it's showing this red curve here, which is the Fourier sum or Fourier series that it's fitted so far, and the white curve is the actual triangle wave. So even with just one cosine wave, we're doing a pretty good job approximating this triangle function. But then if I show, then I let it do another wave, it turns out it doesn't do kind of a twice-a-day wave. It goes from once per cycle to 3 times per cycle. And the red curve gets a little bit closer to the white pure triangle. And then if I add more terms, you can see the amplitude here is actually pretty small compared to that one and that one. And the red curve is getting even closer to the triangle. And the more and more terms I add, I know these amplitudes are hard to see, but some of them are really not zero. The red curve actually ends up being a really good approximation of that pure triangle with sharp corners. So let's listen to what it sounds like. This might be even more annoying than the sine wave, so get ready. Okay, let's go back to sine wave just to compare. And now let's try listening to what it sounds like without those higher frequency terms. So I'm going to decrease the number of terms, and we'll see what it sounds like. Pretty much the same. So it kind of sounds less bright as you get fewer and fewer waves. So that was fun for a triangle wave. Let's try a square wave. And we'll decrease the number of terms. So if I wanted to approximate a square wave with a plane sine or cosine, this is about the best I can do with one wave. And then with two waves, I can stay closer in the middle. And then 3 and 4 and 5 and 6, etc. So I get better at staying in the middle, but there's always this kind of like 9–10% overshoot, which is called Gibbs phenomenon, which is also interesting. So let's go and listen to what a square wave sounds like. At first it'll only play the approximating sine wave, and then we'll add more terms and see how that sounds. Sine wave. So you can hear it sounding brighter and brighter, maybe even more annoying as we add those higher frequency terms. So then let's try a sawtooth wave, and we'll decrease the number of terms. So if I wanted to approximate it with one sine wave, it would be that, and then like that, and that, and that. So it gets to be better and better approximation. So let's listen to this. And you can see how the spectrum is showing me how much power is in each little wave. Old synthesizers from like the 60s and 70s, 1960s, 1970s, would generate instrument sounds by generate something like a sawtooth wave and then filtering out the parts that made it sound not like a clarinet or not like a flute or not like a trumpet. So that was called subtractive synthesis. We can play with this a little bit more. Let's go back to a sine wave. What if I pass the sine wave through a one-way valve so I only get the positive parts? Let's listen to what that sounds like. That's called rectifying or half rectifying. So let's show more terms here. So there's the sine wave. We're going to half rectify. And then you can see we're getting a pretty good approximation here. Let's see it without the without all the high order terms. Even with two terms, that's pretty good, right? And then next we're going to try a full rectify. So we're going to do sine wave and then basically take the absolute value, and you can do that using electronics and diodes and stuff. Let's see. So no, we want to do full rectify. So that's what it's going to look like. What do you think it'll sound like? Let's go back to a sine wave and then rectify it. Did you notice the frequency jumped? Because now we're having basically having two full cycles in the space of what used to take one full cycle. So that's kind of interesting as well. All right, I think that's enough falstad, and we'll go to another app next.